So this question has been asked several times of me. Apparently it's been going around and a lot of people can't settle this as to who wins. So, who's fighting? Well, we have half of a Magma versus 1 Quintillion Eels. That's a 1 with 3, 6, 9, 12, 15, 18 zeros after it. All right, so in order to start this, in order to figure out this, we need to sort of define what our fight is. Well, what is half of a magma? Well, we know that if this is the Earth, then the Earth has the crust on the outside, and then we've got, around that, we've got the mantle, and then within that, we've got the core. Now, the core is made up of liquid, but also a solid hunk of iron and nickel in the middle. So what we're going to use for our magma definition is we're going to use the outer core of the Earth. We're not going to refer to the mantle. We're just going to refer to the inner core. And since we said it's half the magma, so we're going to say half of the outer core. That's what half of a magma is. Now, 1 Quintillion Eels. Now, a lot of people think electric eels, but I'm just going to go for any normal, regular eel for this battle. Now, I'll explain what a normal eel is in a second. But the question is, how do these two fight? Well, magma is just molten metal, is what it is. And eels are just animals. So when it comes to fighting, well, there's no weapons involved, and there's no real skill involved. So how do you fight an inanimate object? Well, the reason that you would fight this is because this has a lot of energy. So what this is this is a battle of energy. So you have a very large container of energy versus a very large force. And the question is, can the eels withstand, can they absorb all the energy that the magma can give off? And that's really the question we're asking. And that's fine. We can answer that. So, let's clarify what's involved. So, in this corner, we have half a magma. So, how big is the Earth? Well, it's really big. And then we've got the inner core, and then we've got the outer core. Now, the inner core, that's roughly a sphere, and that has a radius of 1,220 kilometers. Now, I'm going to put everything in terms of standard units, so I'm going to tack on an extra 3 zeros and say that that's in meters. And you'll see why in a second. All right, and then to the outer core edge, that's going to be 3,400 kilometers, but I'm going to tack on an extra 3, so that means we have 3,400,000 meters. Now, what we need to do is we need to find the volume of this mass. And both of these are spheres, so we have 4/3 pi r cubed. So we'd find the volume of the outside. So we have 3,400,000 cubed. That's the volume of the outside, and then we have to subtract away the volume of the solid inner core. So 4/3 pi, and then we have 1,220 cubed. Now, for simplicity's sake, since we're multiplying both of these by 4/3 pi, I'll just calculate the difference here and then multiply the 4/3 pi on later. So 3,400 cubed minus 1,220, 3 more zeros to the third, and then we multiply by 4/3 pi. And so our volume is 1.57 times 10 to the 20th cubic meters. But that's the volume of the entire mass, and we're only talking half the magma. So we need to cut that number in half. So the volume of half a magma, 1/2 magma. So we're dealing with a volume that is 7.85 times 10 to the 19th cubic meters. So that's our volume. So that tells us how big it is, but but now we have to figure out how much energy does it contain. And so, in order to do that, we have to ask ourselves, well, how much energy and can it hold and what's it made out of? And so this is made out of iron and nickel. And iron and nickel have what's called a specific heat. And thankfully for us, iron and nickel have almost identical specific heats. For iron, it's 0.45 joules, that's our unit of energy, degrees cube per degree Celsius. And for nickel, we'll say it's 0.44 joules per gram degree Celsius. And so what does this mean? Well, it takes 0.45 joules to raise 1 gram of iron 1 degree Celsius. So in order to figure out how much energy this contains, we need to figure out the mass and we need to figure out its temperature. So for temperature, if you look it up, we've got a range. We can range from 4,400 to 6,100 degrees Celsius. And so since this is an approximation, you can tip the scale in whichever favor you want to. If you want to give the half a magma, put it at a disadvantage, say that the entire thing is 4,400. If you want to put it in the magma's favor, say that it's 6,100. The reason that it's a range is as you go deeper into the earth, it gets hotter and hotter. So this is the temperature on the outer edge. This is the temperature on the inner edge. Now the other thing is to keep in mind that this material is underneath the earth, which means that it's not just a hunk of iron, it's a hunk of iron that's liquefied and under pressure. So the density also comes into play. So our density, that ranges from 9.99 to 12.2 grams per cubic centimeter. Now to change this up, we have grams, that's the unit we want. And we have centimeters cubed. Now if we refer back to that, that refers to volume. But our volume was in cubic meters. So in order to make this work, I'm going to have to convert that. So let's see, I've got grams per cubic centimeter. And to do a little unit conversion, I need to multiply and get meters cubed on the bottom. All right, and so for every 1 cubic meter, we have 100 cubic centimeters. So that means I need to multiply 9.99 and 12.2 times 100 cubed. And what that does is that puts our density into cubic meters. So times 100 cubed. So that means our density is going to range from 9.99 times 10 to the 1 to 3 times 10 to the 6th. And we have 12.2 times 100. And then we have, and that ranges to 1.22 times 10 to the 7th. And that is grams per cubic meter. So what does density allow us to do? Density allows us to take volume and turn it into a mass. So that's what we'll do. We've already got the volume of our half a magma. So now we take our volume, which is 7.85 times 10 to the 19th cubic meters, and we're going to multiply it by our density. This is our volume times our density. And basically, what I'm going to do is I'm just going to try and split that right down the middle and say that our density is 1.1 times 10 to the 7th. And include our unit, that's gram per meter cubed. So that means when we multiply, grams and meters cubed cancel out. So now we have 7.85 times 10 to the 19th. And then we multiply that by 1.1 times 10 to the 7th. And what do we end up with? We end up with a mass of 8.635 times 10 to the 26th grams. So that is the weight of half a magma right there. So now the question is, now that we've got its mass, now what we have to do is we have to take mass and convert that into energy, because that's what this fight is. This fight is all about energy. Can the eels withstand the energy that the magma can give? So, if I look back to here, remember it's made up of nickel and iron. Energy is measured in joules. I've already figured out the grams. That's part of it, but we also have to know the temperature. And that's what we said here. Now, people have different preferences when it comes down to this. Again, I'm going to split this right down the middle and say, all right, well, what's halfway between 44 and 61? That's going to be 52 and a half. So that means I'm just going to take a temperature of, and I'm going to assume that the temperature is uniformly 5,250 degrees Celsius. That's what I'm going to go with. And so now, what happens? Well, if I take my mass right here and I take my temperature, 8.635 times 10 to the 26th grams, and I take 5250 degrees Celsius. Now these two units will multiply, but if I also multiplied specific heat in there, and I'll just split it between iron and nickel and say that it's halfway between 0.44 and 0.45, and it's 0.445. Multiply joules per grams, degrees Celsius. Notice what happens. Grams will cancel, degrees Celsius will cancel, and so what we'll be left with is joules. So this will tell us how much energy the half a magma contains. So if I do this multiplication, 5 times 10 to the 26th times 5250. And so what we have is 2.017 times 10 to the 30th joules. That is our energy. That's what this brings to the fight. So now the question is, can the eels withstand that? So let's go away from the magma for a minute and let's think about the eels. Eels don't have any skill. They don't have any fighting ability. All they have is their size. They're just going to overflow and overwhelm the magma. The question is, can they contain it? Well, how big is an eel? Well, eels can range anywhere from the tiniest eels that have been discovered are 1 gram, and they go all the way up to over 100,000 grams in size. That's the eels that grow to be that size are what are called the European congers, if you want to look them up. Now for me, I'm trying to split this down the middle evenly, because not every eel is the size of a European conger, not every eel is the size of a 1 gram eel. So let's say that we go with 50,000 grams as our mass. All right. Now, what are they made up of? Well, they're made up of flesh, but like most fleshy creatures, the majority of what makes them up is water. And there's one very unique characteristic about water. Water has a very notoriously high specific heat. And that's the one advantage that these eels bring to the fight, is their specific heat. And I'm going to assume that the entire eel is made up of nothing but water. Now, that's a bit presumptuous to say, and it does tip the fight in the eel's favor, but that's okay. That's 10 times the heat that it takes to heat up the eels. Hopefully the eels can drain off enough and still hold out. All right. Now, we already got our grams like we did before with the magma, but what about the degrees Celsius? Well, did a little digging, and eels can live anywhere from 4 to 25 degrees Celsius. So what number do we want to pick? Well, I'll try and pick somewhere in the middle. So I'm going to pick, 25. So that's roughly 15 degrees Celsius. All right. Now, there's no point in figuring out how much energy the eels have because they're not the ones giving off energy. They're the ones receiving energy. So now we figured out, here's the mass of one eel. So I guess I forgot one little thing. Times 10 to the 18th. Because there's a quintillion of them. So let's see, 19, 20, 21, 22. So they bring 5 times 10 to the 22 grams of mass. Now we're going to assume that they're made up of entirely water. Not true, but it puts the fight a little bit in their favor. And we're going to say that they come in with a temperature of 15 degrees. So this is the eels. So now the fight. I said that this fight is an energy fight. So what's going to happen? Well, if you ever watch those martial arts movies and you see the one guy, he's ganged up on by 10, 15, 20, and what do? Well, they all fight him one at a time. And everyone gets mad at that. No one likes that. Why? Because, well, just gang rush him. Let's assume that the eels do the same thing. Let's assume that all the eels just gang rush the half of magma. Well, what'll happen? Well, the magma is going to lose energy, and the eels are going to gain energy. So how do we figure out energy? Well, we do what we did. Specific heat times the mass. And what's going to happen is the magma is going to lose some energy. And the eels are going to gain some energy. And so what's going to happen is the magma is going to go down in temperature, and the eels are going to go up in temperature. And what'll happen is eventually the magma and the eels will meet at some temperature, and then the fight will be over. The question is that temperature going to be low enough that the eels can survive? Or is that temperature going to be so high that the eels just incinerate? And that's what we're here to find out. So let's put in what we know. So going back to our magma, the magma's specific heat, we've got 0.445. What was the mass? Let's see. We said that the mass was 8.635 times 10 to the 26th in grams. And we said, what was their normal temperature? 5250 minus x. And x, that's just going to be what it settles on. So on this side, for the eels, the specific heat, that's going to be 4.184 times their mass in grams, 5 times 10 to the 22, times their normal temperature, I'm going to say 15 plus x. Okay, so what we have here is we just have a very simple linear equation to solve. It just has a lot of big numbers involved, but that's okay. All right, so we have 0.445 times 8.635 times 10 to the 26th. Okay, so what we have is 3.84 times 10 to the 26th. And we have 5250 minus x. And so over here we have 4.184 times 5 times 10 to the 22nd. So we have 2.092 times 10 to the 23rd. And what we're saying is that this right here, this represents the amount of energy the magma loses. This represents the amount of energy that the eels gain, and they're equal. Temperature doesn't go anywhere except from the magma to the eels. Now, one thing we can do to help make this problem easier is to say, well, we're just multiplying by these really big numbers, 10 to the 26, 10 to the 23rd. So let's scale this down. So what we can do is if we just divide this whole problem by 10 to the 23rd, what we end up with is 3.84 times 10 to the third times 5250 minus x. And then we end up with 2.092 times, the 10 to the 23rd is gone, times 15 plus x. So we've just scaled down our numbers, made it a little bit easier. So 3.84 times 10 to the third, that just means we move the decimal point over 3 places. So 840 times 5250 minus x equals, and then we have 2.092, 15 plus x. All right. So we'll multiply in these decimals. So 3840 times 5250. So we have 2.016 times 10 to the 3, 4, 5, 6, 7 minus 3840x equals 2.092 times 15. We get 31.38 plus 2.092x. All right. So x is on one side, things without x is on the other side. Now if I subtract this 3138 from this, in scientific notation, it's really not going to matter. So 0.16 times 10 to the 7th equals 3842.092x. So now, to get our answer, we just divide 3842.092 2.092, so 2.016 times 10 to the 7th divided by 3842.2. So what we end up with is just x. And so this is our final temperature that both the eels and the magma rest at. 5247.14 degrees Celsius. So after all that, after everything comes together and all that energy is totally dispersed out, everything ends up with a temperature of 5,247 degrees Celsius. For reference, the boiling point of water in degrees Celsius is 100. So that means these eels are far past boiled. They are incinerated. So who wins in this fight? Half a magma wins. Now, I doubt the results would change if you chose some different numbers than I did. They may bring the magma or eels a little bit closer together, but I think, in all honesty, no matter what numbers you picked, even if you gave the benefit to the eels with every step of the calculation, I still think the magma would win. If you disagree, that's fine. You can show me your calculations in the comments below, or if you have any other weird questions you want to see me worked out, type those in the comments below. Thanks for watching.